favorite. So for this reaction, we have just product, no reactants. So we would normally set this up as the initial change, equilibrium, oh no, it'll still work out either way. The change, well, which way is it going to shift? To the reactants, because there are no reactants. But we can't have zero reactants, so it'll shift towards the left. But we know that because of the zeros. This will be minus 2x, this will be x, this will be x, or I should say plus x. This will be 0.01. Minus 2x. Plug it into the equilibrium expression. And then we can get rid of the squares. Multiply the x to both sides. Plus equals oh. Nobody's going to stop me, huh? Just watching me jump off the cliff. There we go. I guess it might be useful to talk about why I stopped when I did. How did I know I did something wrong? I wasn't looking back at like the math that I did. I was pressing forward with reckless abandon until I calculated what x was supposed to be, and I got 0. You see I wrote 0, 0. This was going to be what x is. And then I looked up here and I saw, wait, what's my k value? 0.055. Does that mean I should have more reactants or more products? A lot less than 1. More reactants. Well, here, let me write out, this was going to be the wrong value, 0.004866. So I look at that 0.004866 and I say, all right, I'm going to plug that in up here. That's not going to subtract very much from that. And it's not going to add very much to this side. It looks like I'm going to end up having a lot more products than reactants. I must have done something wrong. And then I look back and I didn't take the square root. 0.055. But now that we have 2, 3, 4, 5, 2. That's almost the same thing. That's actually even smaller. Okay, well. I guess I just got lucky in thinking that that wouldn't work. So if I plug this in then, that's not enough space. I guess that is a lot more reactants than products. And then we can check our answer. Hmm, 0.0488. Did I miss a 4? Oh. That should work out better then. Yeah. Yeah. Right. Shall we do another?
Yes.
Partly because I want to get to small x approximation. I dug a little too deep in Excel today. All right, so we got a reactant, no product. So this means this is going to go to the right. Minus x plus 2x, 0.0250 minus x plus 2x, or just 2x. One of the things you can do on these sometimes is instead of actually taking this on the bottom and actually multiplying those by the 0.36, I can, well, I'm going to square the top because that's not actually helping me any. And then this is 0.36 times 0.0250 minus x. And that helps in this case because even though I'm going to multiply this over here, I can just take this. It's a lot easier to do just 4 divided by 0.36 instead of multiplying this by all of these things and then doing all the subtractions and getting numbers with lots of decimals. And that 4 divided by 0.36 is 11.1111 repeating. And then this is just 0.0250 minus x. And if we move everything over, That's a nicer quadratic equation. This is 11.111 negative 0.0250. Oh, no, negative 1. Positive 1. And two values of x, 0.020383, and then the other one's negative, so we don't have to worry about that. Oh, right. So N2O4, 0.00462, NO2, Are there any questions?
Why do you not worry about the negative?
Oh, the value of x from the quadratic that's negative, because it can't subtract a negative mass. If you figure out antimatter, that'd be big. So it is always nice when you get a negative value from the quadratic equation, unless you made a mistake in the quadratic equation, you can just ignore those. If you get two positives, then you check and you look at what you're subtracting from, right? Because you're always going to be subtracting from one value. So if I got two x's and one of them was larger than 0.025, I can't subtract more than I have. So then that's the value that you toss. If you get two values that don't work, then you probably made a mistake either in the quadratic equation or before the quadratic equation. Haven't seen it happen yet. If I find one, I'll let you know. No question. Okay. No questions makes me nervous. So we can do these because we can do my brain is running real slow today. Because we can do the equilibrium expression with atmospheres, we can also do ice tables with atmospheres as long as all of our species are gases and we're given Kp, right? So the equilibrium constant for pressure. Although in this problem, even if this was Kc, it would be the same thing. How do I know Kc and Kp are the same? That is important. There's something else though. Specific. Yeah. The number of moles in the reactants versus the products doesn't change. So I've got 2 moles of reactants, 2 moles of products, because the Kp equals, yeah, Kc times RT raised to the change in number of moles in the chemical equation, moles of product versus minus moles of reactant. So since those are both 2, then this delta N is 0, and the RT doesn't matter, so Kp and Kc are the same. So we can just proceed, regular ice table. Initially contained both reactants, each with a partial pressure of 0.15 atmospheres. And none of our product. So now before I write it, I want you to try to write out what would the equilibrium expression be, including our really set of equations that we came up for the concentrations at equilibrium. So should be able to do that pretty quick. So here's what I have. Now, if you don't have that, or you have something different, then hopefully you have a question as to how I got it, why I have it that way. As long as the question's on topic, there's no such thing as a stupid question. Don't ask me what I'm going to have for lunch. I said, I don't know if I'm caught up on Demon Slayer, but I said as long as the question's on topic. Nope, everybody got that? Okay, all right. If you didn't get that, you just don't want to ask in front of anybody, write it down and ask during office hours. Okay, so I squared these because it's the same thing times the same thing, and if I get squared over squared, then I can take the square root of both sides. Because I don't want to do quadratic equations. I'm actually going to square this now, or take the square root. That's okay. know if that really saves me anything. It does make it a little easier to type into my calculator. Nope. Plus 1.5. X equals 0.122850. Yep, and that makes sense.
Where did the minus X go?
Here. So because this is minus X and this is some decimal X, I'm gonna add the 1X to both sides.
Mm-hmm.
Turns out that happens a lot. Where you're just adding, you've got some decimal and then you're adding a whole number of X to it, which kind of makes sense because we usually end up with something like 2X here, which then gets squared and becomes 4, or it's 2X and we can take the square root like this. So you're like adding 2 or adding 1. And then you should always check your answers, because how many other problem types are there where you can directly check your answer? It's a feature, not a bug. Yeah. Yeah. It's like how I got from here to here. I used the polynomial solver on my calculator.
Okay.
Otherwise, you plug in. I have to look up the quadratic formula because I have not used it at all this semester.
Plus or minus the square root of
B squared minus 4 AC over 2A? Yeah. So this will give you two numbers. Still in my calculator. So one of them is, yeah, right? X equals. So my X1 was the 0.020385. X2 was negative 0.110384. And I knew it had to be this one because it's negative. It can have negative mass or moles. And then again, if you had two positive values, actually even if this had been a positive 0.11, that doesn't work over here because I'm 0.02. I can't subtract 0.1 from that. I'd get a negative number. So, and again, I don't know if I've seen, I haven't yet seen one where you get two values that are possible for X. It probably happens, but I'm not sure what parameters you would need to make that happen. It just means that I have to make sure that any problem that I write, I need to actually run it all the way through and make sure that doesn't happen. Because with my luck, I would write a problem that would do that on the test. Yeah, good question. Any others? That was another hand. Yeah. Yeah. Because I'm not paying attention. It's a good thing I'm not going skydiving today. Or doing a lab. That's probably good. Some days you wake up and you're just accident prone. And life advice, if you're ever in the lab and you are just accident prone that day, take a break. Go get a drink of water, go on a little walk, relax, and then come back. If you are working in a lab, then maybe take the day off. Just happens. Any other questions before we talk about approximating for small x's?
Like, make question, like, you put like for maybe meters, it's not supposed to be 3, or it doesn't matter.
That's supposed to be 3. Dang it. I wish this was a bit that I was doing to show you that it's okay to make mistakes, but it's not. I am just making a lot of small mistakes today. That's life. Did I forget a 0? Oh my gosh. All right. Did I make any other mistakes? No, I'll fix it. I'll fix it. This is what I'm talking about. Okay. No, because it's good. I need to make those fixes because I don't want somebody to walk away thinking that that's the right number of sig figs. Or you write it down and then you come back to it later, having forgotten all of this context of how many mistakes I made today, and think, why was it that way? All right, let's talk about simplifying approximations then. So if you were in lab yesterday, we did talk about this already. When you have a very large or very small value for K, equilibrium constant, we can assume that the side that the equilibrium favors is not going to change very much when the equilibrium shifts. And in making that assumption, we can simplify all of our calculations. But that doesn't always work, and so we'll talk a little bit about like when that does kind of work. And then at the end, you always need to check and make sure that your assumption was correct, that you can assume that it doesn't change very much because the amount that it changes by should be 5% or less to be valid. And I know this says if the K is just if the K is small, but if the K is large, you can actually use this also. So like in this problem, we've already got ice table and everything set up. And if we calculate the equilibrium concentrations, we can actually just do, well, I'll do this both ways and I'll do it quick. So if I do, this will be 2x squared over 1.0 minus x. equals 3.3 times 10 to the negative 5. This will be 4x squared plus 3.3 times 10 to the negative 5x minus 3.3 times 10 to the negative 5 equals 0. Oh, no, I need another polysolve. This is going to be 4. This is going to be 3.3 5. So x equals 0.002868. So if we solve this problem exactly, that's what x is going to be. So 1.0 minus 0.002868 is 0.997. 1, which we have like pretty much just 2 sig figs here, ends up being 1.0 still. So that's just to show you, if we solve this exactly, the amount that this changes by x is really, really small. So instead of writing this out and having this x down here, which having x here is the reason I get x here, which is the reason I have to do a quadratic, I assume that this is practically 0. It's not changing by enough to matter, and so I can leave it out. And what that lets us do, I'm going to just, oh wait, I want to duplicate the page. I have to do it this way. So if we approach this problem again, but wait. I do want that part. But instead use a approximation, I could say this is basically 0. And then I'm solving 4x squared over 1.0 equals 3.3 times 10 to the negative 5. Which anything divided by 1 is itself. So this is 4x squared equals 3.3 times 10 to the negative 5. 3.3 e negative 5 divided by 4. Is that now negative 6, and then the square root of that. X equals 0.002872. And when we're assuming that x is 0, when we're approximating x to be 0, it is always just the x that's being subtracted, right? Because this x that I'm subtracting from 1, compared to 1, it's approximately 0. Over here, I'm adding 2x to 0. There's no number that's too small to be insignificant compared to 0. So we're not saying that x is 0 for all of the places that we have x. It's just in that one case. And now when I do 1.0 minus, or 1 minus 0.002872, this is still 0.997, which will still round up to 1. This will be my x times 2. which will be 0.0057. But we do also want to check and make sure that we have a reasonable assumption. We want to make sure that it's okay to assume that x is small enough to ignore. And so what we want to do is we want to compare, take my 0. Let me do this in a different color. I'll take what I calculated for x, 0.002872, and divide that by my concentration that I'm subtracting it from. Multiplied by 100. Which, because we're dividing by 1, this is 0.29%. And the sort of approximate rule of thumb for where the cutoff should be in making this assumption is 5%. So this is a lot less than 5%. This is a safe assumption to make. And so we can treat these values that we calculated as being correct. And actually, this problem might be, oh yeah, so like if we compare, I've got one of my x's down here, the other x that I had up here. I mean, to 3 sig figs, they're the same. The larger this percentage is, the more that your approximate x will be different from the exact x. But as you can see, for 0.29%, doesn't matter. Up to 5%, still doesn't matter. One of the things we did yesterday, but I won't do today, is what happens if you do your small x approximation and you get an x that is more than 5% of the initial concentration you're subtracting from. And you can take that x and just plug it back in. So if this x was bigger than it needed to be, I plug it back in here where I assumed x was 0. I plug that in there and I solve for this x. And as long as I can do the 0 approximation one time, repeating this ends up getting you closer and closer to whatever the true value is, until you get less than 5% between your repeat x's. I really wanted to show you this because the rule sort of here, we're going to go a little bit out of order. Yeah, this is what I wanted to look at. So like, how small is small enough that we can assume? There's two things that matter here. Remember, we're comparing x to the initial concentration of something. So if I have a small k, that means this is going to favor the reactants more, which in this case is A. And I've got here 0.25 moles of A or 0.0025 moles of A. So what I did was I actually took all of these and I calculated them and graphed them. So up here we've got the, which unfortunately this is not going to make it onto the video, but I've got K of 1 times 10 to the negative 5 and my initial concentration of 0.25. And I said, well, what happens as that concentration decreases? So as it drops by 0.05, 0.05, 0.05, you see this percentage gets larger. Now down here, this is the starting concentration of 0.02 or 0.25. And as I decrease the concentration of A, that percentage of X that I calculate becomes a larger and larger percentage. And that's exaggerated even when we go over to this other graph, where now my initial concentration is a lot smaller. What happens to the percentage? .36% or 0.316, and this is 3.16%. So a smaller starting concentration means that my X is going to be a larger percentage of that starting concentration, even for the same value of K. But if we use a different value of K, so I guess out of these two, which one is more likely to work? Or I guess what a larger initial concentration, is a larger initial concentration better or more likely to work than a smaller concentration? That was kind of a leading question. Yeah, so the larger our initial concentration, the larger the number we're subtracting from, the more likely we are to be able to do this small x approximation. The other factor here is K. Plus. So we go down here, I have the same initial concentrations, but now two different values of K. And K has a much bigger effect because if I have a really, really small K, that's really going to favor my reactants. So here, if I move to times 10 to the negative 2, this 0.25, even that doesn't meet my criteria for a small approximation because this x is 10% of that starting value. And then it gets worse as you go down. But if I take the two worst factors, if I've got a not so small K and a really small initial value, this starts out at 100%, which means that if I do this small x approximation, I end up with 0 for my initial concentration. And then I end up subtracting more than my initial concentration, the smaller the concentration gets. So generally, if you have something that's around 0.1 and a K of 10 to the negative 3 or less, oh, actually I want to know what 10 to the negative 3, what is this? 1e to the negative 3, does that work? That works. So you're generally going to be looking for a K of 10 to the negative 3 and a concentration of about 0.1. Actually, look at that. 1 times 10 to the negative 3, 0.1, that's exactly 5%. So, for this reaction, which one is most likely to work for the small x approximation? We want a large concentration, small k. Yeah, so A is most likely to work. We don't really have time to do anything else unless we wanted to look at this other graph. It's not really ready. Okay. I have office hours right now. I also have office hours from 1 to 2. If you have questions about labs or other things,